So welcome everyone to today's session of Seminario Flotante. I'm very happy to introduce Juan Felipe Carmona. He's right now a postdoc at Universidad Nacional de Colombia, and he will be talking about definably amenable groups in continuous logic. So thank you, Juan Felipe, for accepting the invitation, and the screen is all yours.
Okay, thank you very much, Dario and Andres, for inviting me to give this talk. So yeah, I'm going to talk about definable amenable groups in continuous logic. This is joint work with Alphonsus, and this is the outline. So basically, I'm pointing 2 hours convincing you that the definition of definable amenability for this context in continuous logic is the right one. So first I'll have to introduce some notions of amenability in the classical context, in the non-logical context. So that will be the first part. Then I will mention some results about definable amenability in first order logic. And then I will introduce the definition in continuous logic, some results in that context. Then I'll talk about randomizations of definable amenable groups, which are metric structures. So it's like they are groups in continuous logic, and they have this property that I am going to talk about. And finally, I'm going to say some results about F-generic types and their relation with definably amenable groups in this context. So, okay, so first, what are amenable groups? This has nothing to do with logic. Just I take G any group. So if I'm talking about discrete groups, and then G is amenable if it has a finitely additive measure, which is G invariant. Okay, so I am able to measure all the subsets in G, and that means that G is amenable, and this, of course, this has to be G invariant. So if I take a translate of this subset, its measure is the same. For locally compact groups, I can do the same. So this group will be amenable if there is a finitely additive measure on all its Borel subsets, which is G invariant. And I had to add an additional condition, which is that the measure is absolutely continuous with respect to the Haar measure. But again, I'm able to measure subsets. Okay, so that is the idea in this discrete context, that amenability is that I'm able to measure subsets of the group. So these are some examples for the discrete case. All the solvable groups are amenable, but in contrast, the free group, the free non-abelian group in 2 or more generators is not amenable, the same as with the special orthogonal group in 3 or more dimensions, not amenable, and this has to do with the Banach-Tarski paradox, but I'm not going to talk about this, just to give you some examples. And in the locally compact case, all the compact groups are amenable. Okay, now if we are in a general topological group, then the definition of amenability changes. So the idea is that in this case, we don't want to measure subsets of the group, but rather functions that are Reilly uniformly continuous. So this is the definition of Reilly uniformly continuous of a function. Is that for every epsilon there is this neighborhood, such that if 2 elements are close with relation to this neighborhood, then their images are close as well. And a topological group is amenable if there exists this function, which I'm going to call a mean, such that it is linear, positive, and the mean of the constant function 1 is equal to 1. And of course that it is G invariant, okay? So this is the right notion for the case of topological groups. The natural one will be to measure the Borel subsets, but in this case it doesn't work, and I'm going to explain very briefly why this is the right notion. But okay, so the idea in the continuous setting is that we want to measure functions rather than sets, and this aligns with the context of continuous logic, in which predicates are functions. So these are some examples. I won't enter into details unless if you want to know a little bit more about them, but these all are amenable in the general sense, and of course all of the 5 examples that I choose are not locally compact. So it's like they satisfy the general definition of amenability. Okay. In all the cases, amenability is equivalent to the fixed point property, which is that if G acts on certain compact subset that has these 2 characteristics, X is compact, convex, and the whole space is locally convex, then there is a fixed point. So whenever G has this fixed point property, then it is amenable, and vice versa. And this motivates the definition of extreme amenability. So a topological group is extremely amenable if any action over a compact subset, over a compact set is it has a fixed point. These are the canonical examples, but I want to stress this one because it has to do with randomizations. So whenever you take a locally compact amenable group, then the group of measurable functions with domain the interval 0, 1, which is like it's called also the Borel randomization. This is extremely amenable. And sorry?
Yeah, just want to point out that you need more than just 3C on the second example. You need for the class to be Ramsey, basically.
Okay, so here.
Yeah, not for
in order.
Yeah.
Okay, thank you. Right. Yeah, I learned this example from you, and I forgot all the conditions. So thank you, Rafa. Okay. So these are the examples, and if I have a locally compact group, then it cannot be extremely amenable. But the point is, randomizations of amenable groups are extremely amenable, and we expect the same happens in the logic context. Okay, so now let's move to the first order logic. So in this case, I'm going to fix a model in a complete theory T, and G a definable group. And from now on, G will always be a definable group in first order and in continuous logic as well. Definable group in the strong sense, in like, I mean, in the continuous setting, definable as a definable set. Anyway, so G is definably amenable if there is a Kessler measure that is G invariant. It's basically this. I can measure all the definable subsets of G, and it is invariant under the translation of G. So these are some examples. All the stable groups are definably amenable, pseudo-finite groups are also definably amenable, and compact matrix groups in the real closed fields are also definably amenable. And in contrast, the special linear group is not amenable. Okay. There is this nice characterization in NIP theories, which we tried to mimic, and we have some partial results towards that direction. So the characterization is this: G is definably amenable if it has certain type, which it is called F generic, and the type is F generic if it doesn't fork over a fixed model M, but neither it, neither any of its translates. So for every G, GP doesn't fork over M. And this holds for any NIP theory. There is one direction that holds also for NTP2, which I think is, if G is definably amenable, then it has an F generic type. This also holds for NTP2, but that's as far as we can go. So this is the map so far. In the discrete topological sense, we measure subsets, the same with the first order case. But in the continuous case, we want to measure functions, which are uniform and bounded. So this will be like the natural definition for continuous logic, that we are able to measure the predicates, which are indeed uniformly continuous and bounded. Okay, so let's move now to continuous logic. I'm going to fix a complete metric structure and predicates. I'm not going to restrict to the interval 0, 1. It is convenient to allow predicates to have values in the reals. I mean, they are all bounded, so each one in particular will have an interval, like a closed interval. But in general, this is not 0, 1 is not bounded, and this allows us to see, for example, the definable predicates as a Banach space, and also we can see types as functionals, actually as means. So the usual definition is the type of A over some model F over some model M is the set of all the predicates in which the value over A is 0, but this turns to be the kernel of this functional, defining as this. So every element is a functional over its sets of predicates, and actually it's a mean, like it is positive, and the value on the constant function 1 is 1, of course, so it is a mean. And so we can think about types as usually as the set of predicates in which A is equal to 0, or as a realized mean, which is the definition that I like the most for this context, types are realized means. And another definition, so definable group G is definably amenable if it has a G invariant mean on this set of functions. Okay. So we proved that the following are definably amenable. Again, all the stable continuous groups are definably amenable, and the same with pseudo-compact groups, because the same as pseudo-finite. This notion is closed under ultra products, and since compact groups are amenable, they are indeed definably amenable, so pseudo-compact groups are as well. And for example, if I take the unitary group of the ultra product of the finite dimensional linear spaces over C, since the unitary group is definable, this turns out to be the same as the ultra product of the unitary groups of each component. And since these are compact, the group is definably amenable, but it is not amenable because some big result that this ultra product is not nuclear, then its unitary group is not amenable with, actually with the weak topology, but if it is not amenable with the weak topology, it cannot be amenable with the metric one, with the metric topology.
Oh, Felipe, okay, I'm a little bit confused. So what's the language in this example?
The language of C-star.
Or like when you see these unitary groups as groups, you see them in which language?
With the product of
Just,
the C-star.
okay. And you take the ultra product in the metric sense?
Yes.
Or you take, okay.
In the metric sense.
Yeah, okay.
Okay. Okay, so I have this nice example of, so this shows that this is at least a new notion, not only I'm taking the usual amenable groups, but this is something new. And as I mentioned before, types are means. So this suggests the definition that G is extremely definably amenable, or maybe the opposite, I don't know what to call it, definably extremely amenable, if it has a G invariant type, which is yeah, maybe in the first order case, to say that a group is extremely definably amenable if it has a G invariant type, it sounds a little bit, I don't know, weird. But in this case, I think it makes more sense. And I will show that in fact this is the good notion, like in the sense that every action in certain sense has the fixed point, has a fixed point over compact groups. Okay, so okay, so this is what I'm going to say next. So this is the definition. If it has a G invariant type, but what I want is that a group is extremely amenable if every action over a compact set has a fixed point. In this case, it will be a definable action, so I have to define what is a definable function in this context. So I'm gonna take D a definable set and K compact Hausdorff space. So a function from D to K is definable if for every closed and open sets inside K, C contained in O, there is a definable predicate and some epsilon such that the preimage of C is contained in the elements in the kernel of P, which is contained, of course, in P of x less than epsilon, and this open set is contained in these preimages. So this is like in the usual case, but in the usual case, in first order, I don't have to add these two conditions, just take any definable set between the preimage of the closed and the open subsets. That will be definable, but here I have to separate them as in here. And I have this, this characterization. So a group G is extremely amenable, extremely definable if every definable action over a compact space has a fixed point. And by definable action, I mean that if I fixed a point here, then it produces a function from G to K, and that function is definable. And if I fix if I fix G, then the function from K to K is continuous in the usual sense.
Juan Felipe, a question, an actual math question. Sometimes you can approximate compact sets, like embedding them in 0, 1 to a certain kappa, okay? And is the theorem true if instead of for all compact K, you ask just for the metric ones? Because somehow, well, maybe you can approximate it by metric ones or something like this. That instead of just if and only if this happens for all compact, maybe it's enough to ask it for compact metric. I know it's a smaller family of compact sets, but maybe you can do a trick by embedding your compact in 0, 1 to the kappa and maybe doing a metric approximation. I don't know, but maybe it's true. Any feeling about that result?
Yeah, no, this is true, but actually this will be because the space of types is metric, right? It's a metric space.
Yes.
So, and the proof goes
to the space of types. Okay.
To the space of types, and I only need that the action of G into its space of types is
has fixed
point.
Okay.
Yeah. So yeah, it is basically the same proof that the point is that the action over the space of types is an initial object in this category of definable flows. So if the initial object has a fixed point, then all the others will have a fixed point as well.
Okay.
This is basically the proof. So if I take any k, since the action is initial in this category, then the fixed point here, the image of this fixed point here will be fixed point here. So this is the proof basically. But of course I have to prove that this flow is universal. The proof is basically as in first order. Yeah. Okay.
Sorry, your the G between the spaces of types, it's defined this way, or is it?
The action of G
Well,
where
the G is given below, right? Or between K and K. So the question is, how do you pull it up to the spaces of types?
Sorry, I don't understand your question. Okay, can you repeat it?
Okay. So, okay, doesn't matter. Continue. Maybe I'll ask you later.
Okay, but what I'm trying to say is, if I know that G has an invariant type, then the action of G over its space of types has a fixed point. So the space of types has a fixed point, but also the space of types is an initial object in the category of G definable flows. So if I take any other K, and since this action is universal, then there is always a function from the space of types to every K that preserves the action of G. Then if I take the fixed point, which is the invariant type, its image is G invariant as well, because G of f of p is the same as f of g of p, which is f of p because p is G invariant.
Okay, so you're actually pulling out, pulling forward the G from S from the spaces of types to itself. The action on the space of types is the one that you're pulling to K.
Yeah.
Okay. Yeah, okay. That was kind of my question.
Okay, great. And I have this nice example of a simple, extremely definable, amenable group in the classic context, but it is illustrative also. So the type of plus infinity is G invariant, clearly. So this group is EDA, but it is not extremely amenable, and which is weird, but because I'm going to show exactly why the natural action that explains why this group is not extremely amenable is not definable. So if I take the action of R into the circle, the usual action by rotations, clearly it has no fixed points, so it is satisfied. But this action is not definable, and the reason is the following. So if I fix S equals to 0, if I fix this element, then I have the function from R into S1, such that to every R it is sent to e to the IR, and this function is not definable because I can take, so this point here, which is closed, and a small interval open, its pre-image will be something like this. So it's a sequence, an infinite sequence of an infinite discrete sequence, and I cannot add any definable set between the blue and the green. So basically, yeah, by minimality, D doesn't exist. So there is no definable set between the blue set and the green one. So this is not definable. That's, yeah. So this kind of explains this phenomenon. Okay. Now let's move on to randomizations. And as I said before, I expect that the randomizations of definable groups are definably amenable groups are extremely amenable, and we don't have it yet, but at least we have some progress in that line. So yeah, maybe I want to explain. Okay, so if I fix a model M in a first order theory, then the randomization of, or a randomization, because there are several randomizations, but a randomization of M is like a set of random variables over M. So it is built from a set of functions from 0, 1 to M, for example, which are measurable in the sense that the pre-image of definable sets are measurable in 0, 1, and the Borel subsets here, and there is some distance defined as here, like the measure of the symmetric difference of x and y will be the distance between these subsets, and the distance between these two functions is the measure of the set of points in which they differ. And this way, actually, it is a pre-metric, then I have to take the quotient, but this is the idea. I don't want to give too many details. Basically, the randomization is a set of random variables over a discrete model. Yeah, I think this gives you the idea, but if something is not clear, yeah, you can ask me anytime and I will explain further. So there is, as far as I know, this was the more general result so far, that only holds for NIP. So if G is NIP and definably amenable, then its randomization is extremely definably amenable. This is proved by Alex and Jorge. And basically, they used NIP for two reasons. One is because the Kizler measure. Okay, I didn't mention this, but when G is definably amenable, one can ask that the measure is not only G invariant, I mean under the action of G, but also M invariant under the automorphisms of some model M. And in NIP theories, this kind of measures are also Borel definable. So they use the Borel definability of the Kizler measure, but also that the measure is well approximated by the average of certain finite set of types. So I just count how many types enter into some definable set, and the measure is well approximated by this counting. And they use this, so we just were able to remove one of those hypotheses in the general context. So for any definably amenable group, doesn't have to be NIP, if the Kizler measure is Borel definable, then its randomization is extremely definably amenable. And of course, I mean, the idea will be to remove A as well. It seems to me that it has to be true. So these are the two questions now, that if condition A is truly necessary. And actually, what about randomizations of non-amenable groups? Because it seems that the randomization of any group is too well behaved. For example, this is somehow related. I'll explain why. This was recently proved by Ben Jacob and Munoz. The randomization of any group, no matter what, no matter if it is definably amenable or not, it doesn't have to be dependent. The randomization is always definably connected. So yeah, extreme amenability implies definably connected always. So it's like in the middle, but I mean, this kind of suggests that the hypotheses that came from NIP are not necessary at all. But yeah. Okay, now I'm going to talk about this is the last result I want to talk about today, the relation between F generics and definable amenability, partially in the context of NIP theories. So, okay, let's assume that I have a definably amenable group and I take a positive predicate. Then I want to build like a qualitative measure on this predicate. I mean, I cannot, as I said before, I cannot measure the subsets of G, but somehow I would like to say if predicate is small or not with respect to this measure. So, okay, so by P bar, I mean this, so I'm going to bound the predicates. This is just for this makes some calculations easier. So if P of X is greater than 1, then I bound it by 1. Okay, and the measure or the infinite measure of Px will be the limit when lambda tends to infinity of the mean of lambda P bounded. So basically, the set of zeros of P is what I'm going to measure, and the idea is if this is small, then whenever lambda is big enough, this will be narrow and narrow until the limit will be 1. I don't know if that idea is clear, but like if this is very small, then the limit of this function should be something like a constant 1. Then its measure will be 1. But of course, I have to write it like this because I cannot switch the limit with the measure because I'm only able to measure predicates, and the limit of these predicates are not necessarily one predicate. Okay. So the set of positive. Okay, sorry, I need another definition. So if I take a set of positive predicates, it is an ideal if it satisfies these 3 conditions. So if P is in I and Q is above P, then Q is also in I. The product of 2 predicates that are in I is also in I, so it is closed under the products, and all the constant functions are in I. And this ideal is S1 if for every A indiscernible set of predicates, if each sum of different predicates is in I, then each one is in I as well. This an S1 predicate. So, okay, so if we start with a definably amenable group, such that the mean is also M-invariant, then the small predicates are an S1 ideal. And this helps us to prove that there are F-generic types whenever there are I-wide types. Like if I have, if I'm able to build a type such that all its predicates are not small, aren't small, then this type will be F-generic, because whenever I have an S1 ideal, and if I have a type that is I-wide, then it is F-generic. And this doesn't assume NIP at all, just that's...
Could you repeat what I-wide means?
Yeah, it means that P basically this.
Okay.
All its predicates are not in I, are not in the ideal. Sorry, this is empty. This is empty.
Yes.
Okay. So this is partially the same as before. So the problem here is that if you have let's say an S1 ideal, then building a type is easy in the classic case, because I don't know, if some predicate doesn't work, then you take the complement and you can proceed like that. But here, here the construction of types is very weird. It's not that simple, like, because there are no complements and so on. So we need to add this hypothesis that there exists a type that is I-wide. Okay. And the other part is as in the classical case. So if G is definable in an NIP theory, and it has an F-generic type, then it is definably amenable. So it is almost the equivalence, but we don't know if it is possible to build an I-wide type always. So we need to require that hypothesis. Yeah, so that's the result, and that's it. That's all that I have.
Okay, thank you very much, Juan Felipe. Are there any questions from the audience? Okay, perhaps if not, I might like to ask a question. So you were mentioning that when you were trying to generalize Bernstein and Munoz results about that if a group is NIP and definably amenable, then its randomization is extremely amenable, right? So we also showed that if the group only satisfies that the Kistler measure is Borel definable, then it is extremely definable, right? Its randomization, I mean. Extremely definably amenable, sorry. But my question is, do you know if any ultra product, any pseudo-finite groups, let's say, satisfy this property A?
No, but actually, I would like to ask James because I'm pretty sure that he knows whether the pseudo-finite groups. Maybe you know about this.
Me, James?
Yes.
I mean, aren't there just stable pseudo-finite groups? Can't remember.
Well, if you have a pseudo-finite NIP group, I guess also it will satisfy Borel definability for the measure.
Right. So that's what I'm saying. That would be an example then, right?
Yeah,
Yeah.
but my question is if any pseudo-finite group satisfies Borel definability for the Kistler measure. So say
So as in, is
have,
there one that doesn't satisfy
no,
that?
I don't know.
Or,
That's kind of my question.
Yeah. Okay, but I don't know. Yeah, like a simple and stable pseudo-finite groups that have that. Yeah. So the question will be, for example, the ultra product of.
Say a linear group on a pseudo-finite field. That would be the best thing. So you have a group of matrices over a pseudo-finite field. Perhaps you can interpret the field. Perhaps you can have these weird things that are simple and stable, and then its randomization is just weird. That we might look for a counterexample if such a counterexample exists. But
Yeah.
I don't know.
do pseudo-finite fields? Oh no. Yeah. Do they have a definable random graph relation on their home sort? I feel like if
I'm not sure if on the home sort, but if okay, well, at the definable random graph, I don't know.
I think
No, I'm not sure.
I
I know there is a definable relation that for certain subset gives you the random graph. That for sure. What you don't know is that if the domain of that set that gives you the random graph is itself definable. Right?
Well, that starts to sound like
no,
that.
wait. But I guess I was confusing something. So you ask specific about pseudo-finite fields or just simple and stable?
Pseudo finite, I think, because
in that case, yes, because you have the Paley graphs. You basically decide whether, I mean, if you decide x is related with y, if only if x minus y is a square, say a non-zero square, that's either a random graph or a random tournament, but it still will be, I mean, there would be sort of a definable random graph if you wish.
Yeah, so I mean, this is Gabe's and Kyle's result that if you have like the random graph at least, you're gonna have very poorly behaved. Well, I mean, okay, that's kind of earlier than that. If you have the random graph, that's gonna be very bad for types being nice in general. That's kind of where, but I mean, that doesn't rule out the possibility. I missed something. Is you just need one particular type, one certain special type to be Borel definable, right? Or is it that you need all of them, all the invariant types to be Borel definable?
That would be a question for Juan Felipe.
Yeah, no. I mean, what I need is for the measure that is produced by, for example, in the case of pseudo-finite groups, there is an invariant, a G-invariant measure that is like the ultra product of the counting measure. And what I need is that this measure is not Borel definable. So that will then
Right.
that may be a counterexample, because if I take the randomization of that pseudo finite group, the type may be not G invariant. Yeah. So that will be like trying to build a counterexample. It will require that measure, the G invariant measure, is want to be more defined. Yeah.
Wait, so I don't remember very well, but do you know under which conditions? Sometimes the pseudo-finite counting measure actually is definable, right?
Yeah, sometimes.
But not always.
Not always.
When is it? What's an example where it's not?
I don't remember. I think if you have the random graph, the measure will be 1/2 to the number of requirements that you have in your definable set. And I think that measure is not definable. But now I'm not sure.
Well, the just the totally independent measure on the random graph by itself.
I think so.
That measure is definable.
Okay, then I have no counterexample. Well, I guess, I mean, if you allow yourself to have things like linear orders, then you have a measure there that is not definable.
Right, but that's not, you're not going to get like linear orders in a pseudo-finite. Well, okay, you might, I guess you could have a linear order in a pseudo-finite group, but there isn't usually.
No, in a pseudo-finite group, you can't. Well, I mean, if you want it to be an order group, no, you can't.
Yeah, no, I don't mean as an ordered group. I literally just mean with an order.
Okay.
Yeah.
Just to be clear, I don't want a counterexample. I want it. So.
Yeah. Right. So I'll ask Gabe Conant, because he knows a lot more about pseudo-finite groups than I do, and he may know.
Okay. So is there any other question from the audience?
Just by curiosity, try to get a sense of what definability actually buys you, in addition to being amenable or all these variants. So you had a slide with a lot of examples, and I didn't stop. That was in the very beginning of your lecture, I think. Yeah. So in the general picture of amenable or strongly amenable or actions, definable actions, how narrow is that, or how wide, and what kind of a strength does that give you? I think your last theorem or the last project kind of points in that direction, but I don't know what if you're given just an action, maybe it's ergodic, or maybe very far away from being amenable, but if you're lucky enough it's amenable, how far away are you then from definable? Or or if it is invariant, what can you do in order to have criteria so that it is definable? This is a very vague question, and from the list of examples it looks very nice, but what else can you say more in general? This is a very non-specific question on this, but maybe you can say something.
Yeah. Well, definable action, ask for definability of an action is very strong. So for example, the action of any set, of any definable set D over its space of types is definable. So okay, now that doesn't. Let me think.
So what if you have, some nice function, some nice group that is acting, and somehow you're kind of close to being the final, like you have some invariant behavior somewhere. How can you, kind of push can you, or make it like definable by pieces, or like all these things where, or adding nice predicates in a way that you don't mess up too much with the language, but you make it definable. Is there, a general sense, this is a kind of naive question, but I'm just trying to get to grips, because I like these, group actions, and but I think it's very tough requirement that they are definable, and so maybe you can get some of these, even if they are not definable, but you have some kind of, approximation to being definable nice enough, or break it into, I don't know, sorts, or there are all sorts of things, but these examples are very nice, but they are, yeah, I think I think I know the second, the third. I don't really know the fourth one, the Homeo of R. That seems to be very nice. But is there any kind of in between, like if you're not definable yet, you can somehow use some of these in a more local way, or something?
Yeah, that's a good question. But
it's a vague question. Sorry, it's a
no,
very vague question.
yeah, no, I have to think about it. But in essence, I mean, I feel they're very different. For example, if I take any locally compact group, then it is not extremely amenable, because there is this action over its stone check compactification that it doesn't have any fixed points. And so all of those natural actions, they cannot be definably, they cannot be definable, I mean, in several examples. Like there are a lot of examples, for example, in real closed fields, that they are indeed locally compact, and if, for example, if they are one-dimensional, then they are always definably extremely amenable, because the types of minus infinity or plus infinity, they are G invariant. So these functions, these actions over their compactifications, they cannot be definable. So, but they are like the natural actions in the topological sense. They are very different. So that's all I can say now about, yeah, that's my feeling about the distinction between those two.
Yeah, that's very nice.
Okay.
Thank you.
Well, if there are no more questions, let's thank Juan Felipe again for his talk.
Yeah, very nice lecture.
And we'll return to the Flotante next week with a talk by Julian Cano from Universidad Nacional. Everyone is invited. Thank you very much for coming, and thank you, Juan Felipe, for the nice talk.
Gracias, Juan Felipe.
Bueno, chao.
Ciao.
Ciao.